stage 3. So the opponent challenged the reporter with problem.
Problem number 4. Shooting robotic.
Number 4.
We'd like to accept. Thank you.
Okay, problem number 4. So the reporter has 5 minutes to prepare. And for each team, please, the opponent, reviewer, and present the reporter. Write your name on the board for the record.
Sorry, review,
Review, please.
reviewer.
Okay, reporter takes the floor.
Honorable judges and worthy opponents, this is Team Me2 reporting problem 4, shooting rubber band. Problem statement says that a rubber band may fly a long distance if it is non-uniformly stretched when shooting. And the statement wants us to optimize the distance that a rubber band with unevenly stretched can reach. And our focus is on investigate the other parameters and maximize the distance. And here's our theoretical model. The rubber bands, well, we stretch the rubber band's volume remains the same. And we can know that we can get this formula. And because the different different contact area of the rubber band and different length of it, it will change the K value of the different thickness of rubber band. And here is our experiment. In the phenomenon, the rubber band is stretched unevenly, and the alteration in elasticity contributes to an increase in its kinetic energy. As the rubber band returns to its original length, the unevenly stretched strings generate a torque, resulting in an angular momentum that propels the rubber band in its flight. And here's our theoretical model. Like I just said, we apply a force on the rubber band so that the K value will be different. And we apply the Young's modulus equation and plug the equation into the previous formula we get, and we modify the K value of it, and we derive the force by applying this formula. And to determine the change in energy during the launch of the rubber band, we integrate the force while varying the stretch length, because the rubber band from the start, and we integrate it from the original states, and consider a normally stretched. If we consider a normally stretched rubber band, the upper bound of this integrate formula is the original length of the rubber band and the stretch length of it, and the down bound is the original length. And this transforms the energy into initial velocity by energy conservation of it. And when we examining the rubber band when it's unevenly stretched, we'll get the upper bound, while the delta x is the unevenly stretched length, and the x is the original stretch length, and the L is the original length of the rubber band. And we'll get this formula. And by also the conservation of energy, we'll get the initial velocity of the unevenly stretched rubber band as this formula. And we also consider the restoration torque after the rubber band, because of its unevenly stretched, and we derive the angular momentum of the unevenly stretched rubber band. And next, we consider the air resistance while shooting the rubber band, and we can see the equation as below. By solving the differential equation like on the formula 13, we can know that the time of the rubber band's flight is like this. And so solving the x direction, we got the final distance will be like this 15 formula. And this is our experiment setup. We place this is our shooting machine, and we apply the bracket and the launcher on the same thing. And in the preliminary experiment, we investigate the K value of the rubber band, and we can, as the figure shows, that it is likely to be our expectation in the previously expectation. And here is our relevant parameters. We use different elongation length and different ratio between the more stretched one and less stretched one, and torsion and spin. And here's the experiment with torsion. And due to the precision, the torsion increases the loss of energy due to vibration, because as we know as we investigate the rubber band while shooting, the rubber band will be like this, and the torsion will, and with the rubber band shooting with torsion, you'll see the distance may be further, and the xy axis might be wrong, and this is the length that we stretch, and this is the distance that the rubber band goes. And about the spin, the increase of angular momentum due to spinning decrease the energy loss, but the difference is negligible. As you can see in this figure, the blue dots are the first are the velocity, and the red dots are another velocity, and the ratio did not change the distance, as you can see in the figure. And another experiment is about the horizontal and vertical spin. We have the experiment about while shooting is that if we want to know that if the rubber band spin with like horizontally or vertically will be different to be the distance of the outcome. And as you can see in the figure, we can see significant difference about the vertical spin and the horizontal spin due to the small surface area, and the magnetic effect does not significantly affect the result. And the experiment about the elongation length is that this is our previously derived formula, and we use different elongation length our theory. And this is different elongation length as previously shown. And here's the boundary condition of the rubber band. When we stretch the rubber band, we don't want it to exceed the elastic fatigue moment, because there's lesser energy restoration of the elasticity fatigue one. So in order to maximize the distance, as this problem statement told us, we absorb the elastic fatigue and put into our theory to maximize the distance. And here is the result. And by using the formula of the elastic fatigue, we can know in this figure that there's theoretical result is 1.487 meters, and our experimental result by it is 16.3. And here's a possible deviation. We think that the temperature might affect the maximum distance of the orbit, but here's the challenging part of the experimenting, so that we use the modified value of the Young constant as below. And while we do the experiment, we also should make sure that every experiment is under 25 degrees Celsius. And it's further future research. And we think that we consider the effect of the change of direction. Although we consider the airflow around the rubber band is negligible, I think it is still worth to analyze how spinning object with minimal surface area affects the airflow. And simultaneously, if we want to investigate the airflow occurring within the region circumscribed by the rubber band is also valuable. And here's the conclusion. We know that initial velocity of rubber band will be as below, as previously described, and with the consideration of drag force, the distance will be like this, and the maximum distance of our theory as shown. Thank you.
Okay, so the opponent is proceed.
First, can you please come to the page, the second page? Can you totally explain me the video? Is to
Like it is our launcher of the rubber band, and we make sure that this point will move, and we have measured points in the launcher, so that we make sure the right ratio we have while uniformly stretched.
And do you think your experiment setup is stable enough, or there is any part of your experiment setup may catch deviation? Like I think the rubber band will hit your experiment.
I think the friction between the rubber band and our launcher might be the experimental deviation while maximizing the distance of the rubber band, but we think that is negligible.
Okay, so the opponent has 3 minutes to prepare. test the floor maximum 4 minutes. Take off your mask.
First, common statement is okay, the rubber band may fly a longer distance if it is non-uniformly stretched when shot. D is when optimize the distance after the rubber band with spin can reach. And our main focus is how to optimize the distance. And next, the reporter structure. First, observation video. They use a gun through the rubber band and a theoretical model. They use Young's model, electric conservation, angular velocity, and air resistance. And about the setup, they use a stick gun to shoot a rubber band. And about the experimentation, they change the length, torsion, and speed. And about the conclusion, they find the initial, they calculate the initial velocity and the drag force. About the strong and weak point. What's the strong point? I think. About the weak point, they are made of comparison between experiment and their theory, and they are not exact suggestion to optimize the distance. And there's a point to be discussed about observation. We are conclusive if their setup is stability. And about the experiment setup, we see the rubber band will hit the experiment, and experiment will hit their stick gun. About theory, how to define the uneven stretch, and second, did I consider the bending, and how to measurement the moment of insertion, and how catch the rubber band stretch unevenly. And about experimentation, the shooting angle influence the distance.
Okay, so the public source floor discussion.
What do you think is the most important parameter in this problem?
You mean how to maximize the rubber band distance? I think it's the ratio between the more stretched one and the less stretched one. And also, as you can see in our integrate formula, and the upper bound and lower bound, you can know that there's greater difference between the upper one and lower one.
Okay.
And
And
yeah, you can see.
then in your data, we can see when the rubber band spin, you can reach the more distance. And how do you see how it works? How the spin maybe flying farther?
Okay. As you can see in this formula, that we can know that this unevenly stretched cause the greater distance of the initial velocity. So initial velocity has a relation between between the max distance.
I mean the speed, not the
Yeah.
initial.
And so that if the unevenly stretched also causes the spin, so we think that this it isn't the energy of the angular momentum that cause the energy to the velocity. It is the unevenly stretched
And how to
restoration of the energy
how
that
to define
causes
the uneven stretch? How
into
to
that.
define the uneven stretch?
Uneven, just by the ratio of both the more stretched one and the less stretched one, and by the ratio we do mean the because they have the same length as you can see in the picture, and this is stretched by the original by the lesser length of the original version. So
And how you control the uneven stretch?
like I just said, in introduction we have marked the length of each dot around the launcher, and we use our hands to pull it to the back of the launcher so that we can control the ratio of it.
And how do you know it's stable?
I mean,
And if we the same every time.
and while we conduct the experiment, we'll make sure that the rubber band up in the end of the launcher will caused by the less friction between it, and we stable the end point of the rubber band so that we make sure that the ratio is what we want.
And I saw you with the integral momentum. And how do you implement the integral of the rotation? Because we send a perfect circle, right?
Yes.
So how do we do it? The I.
We use this formula so that the radius is actually the magnitude of the platform. So that here's our launcher and here's the rubber band. So that we know there's both force acting on it, right? And so we know that the force times the length is the torque that we add on to the rubber band. So we add up to 2 torque and eventually get the angular speed of the angular.
Do you consider about the Magnus effect if you do a spin, right? Do you consider about
Can you see that?
Magnus effect?
Like the presentation I just said that due to the less surface area of the rubber band, we did not consider Magnus effect in this condition. And here you can see that we didn't consider we experiment that the horizontal spin and the vertical spin did not have significant different result of the length of the distance of the rubber band.
Okay, no verbal communications. test notes we don't do.
And also you can see that the magnets effect cause the pressure. You assume that the magnets effect cause the pressure difference between the different cause the different spinning caused by different area. So, but you may see the figure that you can see obvious difference about the
About your something about the LV system.
yes.
How to know the area of this function?
The area of it is the while the rubber band spins, like for example the horizontal one, the surface area of it is the radius of the rubber band and the thickness of the rubber band. But
So it didn't like and after you shooting, you will change to like this, and that area will be different.
yeah, sure, but in this case, like I just said, the area of it is very small, and like there's no, that's why that there's no magnets backing it, so that we just put the acceleration in, but integrate these while the rubber band restores its shape. So that may be our creation of the experiment.
About your data, is there any data about your speed? Is the rotation speed all the same? And that is what?
About the spin one. So that rotation, you mean the rotation speed? I think it's not the same because of the ratio. If the ratio of the more stretched one and less stretched one is bigger, the spinning will act, the spinning speed will be much larger. And like the presentation, like I just said that there's no significant result about the ratio of the spinning speed and the distance of the max distance of the rubber band.
And how this do surfing? By the do surfing.
Yeah.
There should be this, right? To compare.
Time's up, sorry. Okay, so the opponent summarized the discussion.
So first, we still think that the setup need to fix in the future. And then in their theory, they didn't consider about the airflow, and I think it's important for this phenomenon. And also, and like this way, the speed of the rotation speed isn't present the same. I see.
Okay, time's up. Okay, so the reviewer asks questions. 3 minutes.
So first, I'd like to ask both of you, can you please turn to the page of the video? I want to ask is, did the rubber bands obey which one? Did the rubber band obey which one?
You mean orbit?
Just,
You mean the so
just it was F equal to Kx.
I think you can describe by the Young's model. If you want more correct.
It is F equal to Kx for that.
because the k is not constant, so f equal to kx is correct, but the k is not.
Okay. And I want to ask the second question to both of you. If the rubber band, when the rubber band shoot, and if the rubber band is homogeneous, just if it is it will be just if it is around to shoot, or it will be like this.
I think the second one.
But yes, so I agree with your opinion. But-
Why is the reporter?
But the report is use this, but not this. So
Do you mean while flying through air?
yes.
I might say, I didn't remember I have stated that the urban while flying has the circle shape.
But your theory is using a solution. And to do the next question. Why the non-uniformly rubber band is stable?
You mean on evenly stretched rubber band?
Yes. Why is this stable?
I think I did not mention that it is stable, but an uniformly stretched rubber band can cause rare distance of it.
And what did you say?
Okay, time's up. So the reviewer has 2 minutes for preparation. Okay, reviewer takes the floor.
Hello everyone, this is team offices and I'm going to do the review. And according to the topic, we want to find the rubber band with non-unfriendly to shoot, and we are going to find the farthest distance. And there and the theory is consider the air resistance and the changing of the PF3 and the Young's models and the effect of the rotating to get the formula of the and the experiment is use the non-like diplomatic to shoot the rubber. And with the discussion, the opponent asked how the spin make the rubber band fly farther, and the reporter answered is according to the formula of the velocity. How to define and the opponent asked how to define the uneven straight, and the opponent and the reporter and they asked how the spin make the rubber band fly from. And the reviewer asked about if the rubber band shoot, and it would be the homogeneous, and both of them say and the opinions say yes, it is homogeneous, and but the reporter say yes, it is a circle, just a circle. And it is my thing.
Okay, so question for the juries, sorry, to read my, yeah. For the reporter, concluding remarks.
For the concluding remarks, in previous discussion, we discussed the stability of the setup, which is the launcher, and we both considered it as the deviation of the experiment, and that the friction between the rubber band and our launcher is negligible. And next, the opponent asked the reporter to define the uneven stretch, and I think it is shown in the video. And the opponent asked the reporter how to calculate the moment of inertia, and we explained that the torque equals to moment of inertia times the angular acceleration of angular acceleration. And next, the opponent asked us about the experiment of spin, and we stated that the spin speed does not affect the distance. And about the rubber band shape in the air, we did not consider it as a perfect circle in our theory, so it does not matter.
Okay, so question from the juries to each of you. So, any questions?
One question to three of you. So I just wonder, can you really apply Hooke's law in this circuit?
No, because the K value is not constant.
I think no, because the K will change, but we can also use other way to find.
I think no, but because as a reporter stated, K isn't a constant because the rubber bands in area isn't a constant. You are being smaller by your stretch.
Okay, so the stretch. So then, how do you evaluate the force? So because the rubber band would spin, so that is due to some force difference in between the two stretch line and the other side. So how do we evaluate the force which causes the spin?
We evaluate the force by the ratio of different more stretch one and a less stretch one. So we can know the ratio between the force, and we know the K value is lesser in the thick one and the bigger in the thin one.
Okay, so you think that the thicker part has the smaller K and the other side has the larger K. Is that correct? Is that what you mean?
Yes.
Okay. So do you think so?
Yes, I think so.
I'm not sure. I think use the Young's model will be more.
Yes, we can use the, what I do is use the, it's also like we use the Young's model to calculate the force at this side and that side.
Thank you.
I have a question for the reporter. Can you remind us how do you do the optimization? Do you optimize the distance?
We use the integration of the energy restoration of the unevenly stretched rubber band and compare it to the normal rubber band, that we can know that we can take the upper bound and lower bound into consideration, and by deriving the force, by deriving the energy, we can lead to the initial velocity, and in turn leads to the greater distance.
And what is the maximum?
Optimize. How do you get the maximum distance? That is my question.
By optimizing the distance, we calculate the spin, the unevenly stretched ratio, so that we can control it, and we can by comparing the experiment and our theory, get the result.
So you use your theory results and get your experiment result, and these two values are close to each other. Is that what you mean?
Yes.
So the key point is you use the boundary condition.
Because we know that if the rubber band has been stretched for too long, it will experience the elasticity, and it wouldn't have restored energy in it, and so that our boundary condition of it, so we plugged into the distance that we have previously derived, and so that we can draw a line through
Okay,
the.
time stop. Okay. Okay, time for four. Okay.
time for the reporter. Sure, let's go for the reporter. Okay, sorry. No hurry, no hurry. Okay, 57767. And score for the opponent. Okay, 56766. And score for the reviewer. Okay, 44565. Okay. Let's go to do it. So, any comment from the jury to each team?
I do have one comment. I think that this question, the key issue for this question is the speed. Can you think about where the speed comes from? Okay, let us stretch the rubber band to produce the speed.
This is not a question, just the
Yeah.
point.
Also, we have tell you the score, so yeah.
Maybe comment on their performance or what they had. So,
Because why I felt that because this question is give you a hint, the speed is the hint. But during your presentation, I think you are talking about where the speed comes from, how can you use the speed.